Inside a chip colder than deep space, 20 tiny circuits are keeping a rhythm that physics says must die. Scientists ran it again and again. The beat held. Tonight we follow that pattern into a crystal made of time, a particle that remembers being moved, a current that runs one way forever, and a burst of errors fired at us from the edge of the galaxy. If this grips you, hit like and subscribe. Prepare yourselves. We begin. In a windowless lab in Santa Barbara, a machine kept doing something the people who built it had already told it to stop. The machine was a quantum computer. Its brain was a chip the size of a postage stamp, hanging upside down inside a tower of gold pipes and copper shields. That tower is a refrigerator, and it is one of the coldest places in the known universe. The empty space between stars sits about 3 degrees above absolute zero. This chip sat at roughly 1/100th of that. Colder than the void. Colder than anywhere nature makes on its own. Inside the chip were 20 tiny loops of aluminum. Each one held a single unit of quantum information. The team hit them with a pulse of microwaves, flipping them from one state to the other. Then they waited. Then they hit them again. On, off, on, off. A metronome ticking about 1,000,000 times a second. Everyone in that room knew what was supposed to happen next. The loops would get sloppy. Real hardware is never perfect, and the pulses were never exactly right. Each qubit would drift a little further from the beat. Within a few dozen cycles, the neat rhythm would smear into mush, the way 100 clapping hands drift out of sync at the end of a song. Physics has a word for that smearing. It happens to everything, everywhere, always. It is the most reliable process in existence. The smearing never came. The qubits settled into a rhythm the researchers had not asked for. The team was pulsing them once per cycle. The qubits were flipping once every 2 cycles, half tempo, perfectly locked. The chip had taken the beat it was given and answered with its own, slower one, and it held that slower beat cycle after cycle after cycle. They ran it again. Same result. They started the qubits in a different arrangement, a random scramble of ones and zeros, the kind of messy starting point that should destroy any organised behaviour instantly. The half tempo came back, Poe. They tried another scramble, back again. It did not matter where the system started, it found the same rhythm every time. That last detail is what turned a curiosity into a crisis. A trick can survive one starting point. A property of matter survives all of them. What the team was watching had the signature of a property, something baked into the system itself, as basic to it as hardness is to steel. Think about what that means for a moment. Take a box, seal it, shake it with a steady rhythm forever. Everything you know says the contents will eventually turn into featureless soup, a warm nothing where every arrangement looks like every other arrangement. That is the fate of coffee left on a desk, of a dropped egg, of a shuffled deck, of a star. Everything runs downhill towards sameness. Something in that refrigerator was running level. The work came out of a team from Stanford, Google, Oxford, and a research institute in Germany. When they finally published in the journal Nature, they used a phrase that sounds like a joke and is completely serious. They said they had made a new phase of matter: solid, liquid, gas, and now this. To understand why 20 tiny loops of metal caused physicists to argue for the next 2 years, you first have to meet the one law that nothing in the universe has ever escaped. Pour milk into coffee and watch what happens over the next 10 seconds. The white curls into the brown. It swirls, it feathers, it makes those beautiful spiral shapes for a moment, and then it stops making shapes at all. You get tan liquid, uniform, boring. Leave it on the desk for an hour and it also stops being warm, matching the room around it exactly. Now try running that backwards. Sit and stare at your tan coffee and wait for it to separate itself, for the milk to gather back into a neat white blob and the heat to climb back out of the room and into the cup. You will wait forever. Nobody has ever seen it happen. Nobody ever will. This is the second law of thermodynamics, and it is the closest thing physics has to a commandment. Systems move from organised toward disorganised, from lumpy toward smooth, from interesting toward uniform. Physicists call the measure of that smoothness entropy, and entropy in a closed system only climbs. Here is the part that makes it inescapable. The second law is not a force pushing things around, it is a counting argument. There is exactly one way for a deck of cards to be in perfect order, and there are about 80 unvigintillion ways for it to be shuffled. So when you shuffle, you land in the shuffled pile every single time, because that pile is unimaginably larger. Order is rare. Disorder is common. Randomness finds the common thing. The same counting rules the entire universe. A hot cup and a cool room have far fewer arrangements available to them than a warm cup and a warm room. So the warm ending wins, stars burn out. Mountains flatten, batteries drain, bodies age. All of it is the same arithmetic, playing out at different speeds. Physicists have a word for the moment a system finishes that slide and gives up all its structure. They call it thermalization. The system reaches its own private heat death, where every part looks like every other part, and nothing interesting is left to measure. For a long time, everyone believed thermalization was universal for any system with many interacting parts. Bring enough pieces together, let them talk to each other, and they will grind each other into sameness. There was even a formal statement of this belief, a hypothesis at the foundation of statistical physics, and generations of scientists built on top of it. Now apply that logic to 20 qubits in a refrigerator. You're pumping energy in with every microwave pulse. Energy plus many interacting parts equals heating. The qubits should absorb that energy, share it around, and climb toward the hottest, most scrambled state available. Physicists have a grim name for where a driven system is supposed to end up. They call it infinite temperature, which means every possible arrangement is equally likely and every measurement returns garbage. That is the expected ending. Garbage. Google's chip declined. For decades, the second law had faced down every clever attempt to dodge it. Imaginary demons that sought fast molecules from slow ones. Machines designed to run forever on nothing. Every single one collapsed when someone did the accounting properly. The law always won. So when a rhythm appeared in a driven quantum system and stayed, the first assumption was an equipment failure. But there was one direction nobody had thought to check for order, and it had been sitting in plain sight the whole time. Pick up a grain of table salt and put it under a good microscope. You will see a cube. Sharp corners, flat faces, edges meeting at clean right angles. Zoom further, past what any microscope can show you, and the reason appears. Sodium atom, chlorine atom, sodium atom, chlorine atom stacked in 3 directions in a grid so regular it looks manufactured. That grid runs unbroken through the whole grain. Trillions of atoms, all obeying the same beat. That is a crystal, a pattern that repeats in space. Snowflakes do it. Diamonds do it. Quartz, sugar, ice, the silicon in your phone, all of it built from repeating arrangements that lock into place and stay. Something strange has to happen for a crystal to form, and physicists find it beautiful. Before the crystal exists, the atoms are floating in a liquid, and that liquid looks identical everywhere. Move 1 inch left, same thing. 1 inch right, same thing. There are no special positions. Then the temperature drops, the crystal forms, and suddenly there are special positions. Atoms sit here and here and here with gaps between them. The evenness of space has been carved into a rhythm. Scientists call that carving symmetry breaking, and it is one of the deepest ideas in all of physics. A system with no preferred location spontaneously chooses a set of them. Now hold that thought and change one word. Space is not the only smooth thing in the universe. Time is smooth too. This second is the same as the next second. There are no special moments built into the laws of nature. Run an experiment now or run it in an hour, and physics treats both identically. So here is the question that started everything. If a liquid can break the evenness of space and produce a repeating pattern of positions, could something break the evenness of time and produce a repeating pattern of moments, an object that ticks forever, with nothing driving it and nothing running down? Picture a wall clock with no battery, no spring, no plug, no light falling on it, sealed in a box in the dark, and its second hand keeps sweeping. Not because someone wound it, because ticking is simply what that material does, the way being cubic is what salt does. That is a time crystal. Say it out loud and it sounds like something from a bad film. It is far stranger than that, because it is a real proposal with real mathematics behind it, and the first person to write it down had already won a Nobel Prize. The idea also seems to smash straight into the wall from the last chapter. An object that moves forever with no energy going in sounds exactly like the impossible machines that have been proposed and demolished for 3 centuries. Ticking means motion. Motion in a system at its lowest energy means the system had energy left over, which means it was never at its lowest energy at all. The logic seems airtight. And when this idea appeared in 2012, some of the sharpest minds in theoretical physics set out to prove it was nonsense. They succeeded. They wrote proofs. The proofs held up. Then somebody noticed what those proofs had quietly failed to cover. Frank Wilczek was teaching a class on crystals when the thought ambushed him. He is one of the most decorated physicists alive. He shared a Nobel Prize for working out how the strong force binds quarks inside protons, a piece of theory so fundamental it sits in every textbook. Standing in front of students, walking through the ordinary story of how atoms arrange themselves in space, he found himself wondering why time never got the same treatment. In 2012, he published the idea. A time crystal, he argued, could be a genuine state of matter in which a system in its lowest possible energy state still moves in a repeating cycle. He sketched a version involving charged particles on a ring, forever circulating, with no way to speed them up or slow them down. The reaction was fast and it was harsh. Within months, a physicist named Patrick Bruno published an argument that Wilczek's specific ring model could not work. Wilczek pushed back. Others piled in. The idea developed a reputation as the sort of thing a famous person can get away with saying, and a young researcher cannot. Then came the knockout. In 2015, 2 theorists, Haruki Watanabe and Masaki Oshikawa, produced a general proof. Their argument did not attack one model. It attacked the whole category. They showed that any system sitting quietly in its lowest energy state, left alone, obeying the standard rules, cannot produce that eternal ticking. The correlations that would carry the rhythm simply die. The proof was clean. The community accepted it. Time crystals, in the way Wilczek first imagined them, were dead. You could stop the story there and call it a cautionary tale about brilliant people chasing pretty ideas. Plenty of physicists did. Look closer at what that proof actually said, and something interesting appears in the fine print. Every serious proof in physics comes with conditions attached, the way a warranty comes with conditions attached. Break the conditions and the guarantee stops applying. The impossibility proof rested on one big assumption that nobody questioned at the time, because it seemed too obvious to question. It assumed the system was in equilibrium. Equilibrium means settled, balanced, left alone with nothing pushing on it, having already finished all its interesting changes. That is the state where thermodynamics does its best work, and it describes an enormous amount of the world. A glass of water on a table, a rock, a cooling star. It also leaves out something huge. The universe is packed with things that never settle. A candle flame holds its shape only because wax and oxygen keep feeding it. Your heart holds its rhythm only because chemistry keeps supplying it. A hurricane is a structure that exists purely because energy keeps pouring through it. Every one of these things has organized repeating behavior. Every one of them would vanish the instant you sealed it in a box and waited. Physicists call these driven systems, and the mathematics for them is far messier than the mathematics for a rock, which is exactly why the impossibility proof left them alone. A handful of theorists looked at that gap and asked a dangerous question. What if you stopped demanding that a time crystal sit still and be quiet? What if you fed it a rhythm and watched what it fed back? The answer turned out to be far stranger than a clock that runs forever. Push a child on a swing and you already understand the next idea. You give one push each time the swing comes back to you. Push, wait, push, wait. Your rhythm is steady, and the swing matches it exactly, arriving once for every push you give. Now imagine a swing that decided to answer at half your speed. You push twice, it completes one full cycle. You push twice more, it completes another. Your rhythm and its rhythm are locked together, and yet they are different, and the swing chose the difference on its own. That is the shape of the loophole. Theorists working around 2015 and 2016 realized that a quantum system being shaken with a steady rhythm could settle into a state that repeats at twice the period of the shaking, or 3 times, or 4. The system takes the beat it is handed and produces a slower beat that was never in the instructions. They gave it a formal name, discrete time crystal. Discrete because the rhythm comes in steps rather than a smooth flow, since the driving comes in pulses. Physicists call this kind of shaken system a Floquet system, after a French mathematician who studied repeating equations in the 1880s, long before anyone imagined quantum computers. Give a quantum system a periodic push, and the mathematics of Floquet describes what happens next. Here is why the half-tempo matters so much, and it is the single most important idea in this whole story. The pushing has a symmetry built into it. Every pulse is identical to every other pulse, so nothing distinguishes one cycle from the next. The system faces a perfectly even ladder of moments, and then it breaks that evenness by choosing to repeat over 2 rungs instead of 1. It has invented a distinction where the laws provided none. Same thing Salt does with space, performed on time instead. Now for the hard part, the reason this took decades to achieve. Shaking a many-part quantum system is a fantastic way to cook it. Every pulse pours in energy. Those parts talk to each other and spread the energy around. Left to run, the system heats toward that grim infinite temperature ending, where the rhythm drowns in noise along with everything else. Any subharmonic beat you managed to start would last a handful of cycles and then dissolve. So the theorist needed 2 ingredients at once, a system that answers at half tempo, and a mechanism that stops the shaking from cooking it. Finding a material with both, in nature on a lab bench, is close to hopeless. Real materials come with whatever properties they happen to have. You cannot dial the interaction strength between atoms in a rock, or scramble their arrangement to order, or read out every single atom one by one at the end. The theory needed a system where every part could be programmed independently, every interaction tuned by hand, every component measured on its own, and the entire experiment repeated thousands of times with tiny variations. That is not a description of any material. That is a description of a machine. And in 2019, a company in California had just switched one on for an entirely different reason. Google built Sycamore to win an argument. In 2019, the company announced that its quantum processor had finished a calculation in about 3 minutes that they estimated would take the best conventional supercomputer on Earth 10,000 years. The task itself was deliberately artificial, chosen because quantum hardware is good at it and ordinary hardware is terrible at it. Rivals disputed the numbers. Arguments raged for years. While that fight played out, a group of physicists looked at Sycamore and saw something completely different. They saw a laboratory. Consider what a quantum processor actually gives you. Dozens of quantum objects sitting in a grid, each one built to order and each one individually controllable. You choose which ones talk to each other and how strongly. You set every starting condition by hand. You apply operations in any sequence you like. Then you read out the final state of every single component separately, and you repeat the whole thing thousands of times to build up statistics. No experiment in the history of condensed matter physics has ever offered that much control. Study a normal material, and you're stuck with what nature made. You get roughly 10 to the 23 atoms in a lump of metal, arranged however they arrange themselves, and your instruments can only measure bulk properties. Temperature, magnetism, resistance, averages over unthinkable numbers of particles. You can never reach in and set atom number 7 to a specific state. In a quantum processor you can. One of the researchers on the project, a postdoctoral scholar at Stanford, put the shift in thinking plainly. His team stopped treating these machines as the computers of the future and started treating them as complex quantum systems worth studying in their own right. Instead of computation, they used the computer as an experimental platform for creating and detecting new phases of matter. That sentence describes a genuine change in what physics can do. For 400 years, science advanced by building better instruments to observe a universe that was already there. Telescopes for the sky, microscopes for the small, colliders for the deep interior of matter. Every one of them a window onto something that existed whether or not anyone was looking. A programmable quantum processor works differently. It lets you build the thing you want to study. You specify the rules, the connections, the starting conditions, and the machine assembles a quantum system obeying exactly those rules. If the system you describe has never existed anywhere in nature, the machine builds it anyway. Which means physics gained the ability to ask a new kind of question. Rather than asking what the universe contains, you can ask what the universe permits. That is the question the Time Crystal team asked. The rules had been written down years earlier. Nobody had ever assembled a physical system that followed them. They now had a chip that could. But turning that idea into a result meant working with the strangest component in modern engineering. A single bit of information stored in a loop of metal so cold and so fragile that a stray photon can wipe it out. The qubits inside Sycamore are made of aluminum printed onto silicon, and they look about as impressive as a scratch on a window. Each one is a small circuit, a loop of metal, a capacitor, and a component called a Josephson junction, which is a deliberate gap in the metal so thin that electrons cross it without touching it. The whole assembly is maybe 1/5 of a millimeter across, which is roughly twice the width of a human hair. Chill that circuit hard enough, and it stops behaving like a circuit at all. Below a certain temperature, aluminum becomes a superconductor. Its electrical resistance drops to 0. Current flows around the loop forever, losing nothing. More importantly, all those trillions of electrons stop acting like a crowd of individuals and start acting like a single object with one shared quantum state. That shared state is the qubit. It can sit in a low-energy configuration, call it 0. It can sit in a higher one, call it 1. And it can sit in a combination of both at once, which is the property that makes quantum machines worth building. To control it, engineers fire microwave pulses down a wire, the same kind of radiation your phone uses to talk to a tower, tuned to an exact frequency and lasting billionths of a second. The right pulse tips the qubit from 0 to 1. A weaker pulse tips it part way. Tune the timing to a fraction of a billionth of a second and you can steer the state wherever you want it. Now the difficult part. That quantum state survives only while the outside world leaves it alone. Heat destroys it. Vibration destroys it. Stray magnetic fields destroy it. A single infrared photon carrying a whisper of energy is enough to knock a qubit out of its state and turn your careful experiment into noise. Which brings us to the refrigerator. A dilution refrigerator is a stack of metal plates hanging one below the other, each colder than the one above, wrapped in shields, hanging inside a vacuum chamber. It cools by mixing 2 forms of helium and exploiting the temperature drop that mixing produces. The bottom plate, where the chip lives, reaches about 10,000ths of a degree above absolute 0. Put that in perspective. The coldest natural spot ever found in the universe is a cloud of gas in space, where the temperature falls to about 1 degree above absolute 0. This refrigerator is 100 times colder than that. When those machines are running, the bottom of that fridge is very likely the coldest cubic inch anywhere, and even down there the qubits are dying constantly. A typical superconducting qubit holds its quantum state for something like 1/10,000th of a second before the outside world corrupts it. Every operation you perform carries roughly a 1 in 100 chance of going wrong. Stack a few hundred operations and errors are guaranteed, which makes the Time Crystal result even harder to swallow. The team was not working with a pristine, perfect system. They were working with 20 leaky, imperfect, error-prone loops of metal, connected to the outside world by wires, fighting a losing battle against noise every microsecond. And those 20 flawed components produced a rhythm so precise that it did not drift by a fraction of a beat across hundreds of cycles. The question was how they got it to happen at all. The recipe fits on a napkin, which is part of what makes it so unsettling. Start with your 20 qubits and give each one a value, 0 or 1. The team picked these at random, so a typical starting point looked like nonsense. 1, 0, 0, 1, 1, 0, 1, and so on down the line. Now run one cycle, which has 2 moves. Move 1. Fire a microwave pulse at every qubit at once, designed to flip each of them. Every 0 tries to become a 1, every 1 tries to become a 0. Move 2. Let the qubits interact with their neighbours for a set amount of time. This is where the physics gets tangled because each qubit now nudges the ones beside it. and those nudges depend on what state the neighbours are in. That is the whole cycle. Flip, then mingle, then do it again, and again, and again. Run one cycle and the pattern inverts. Run 2 cycles and it should come back to where it started. Flip a coin twice and you get heads again. So the team ran it and watched a specific qubit, checking its value at the end of every cycle. What they saw was a value that went 1, 0, 1, 0, 1, 0, marching in perfect step with the double flip, holding on past 100 cycles. 2 facts turn that boring-sounding list into a result worth publishing. The first is what should have happened instead. That interaction step is a scrambler. Each qubit's fate depends on its neighbours, whose fates depend on their neighbours, and information spreads through the array like gossip through a school. Ordinarily, that scrambling wins fast. After a few dozen cycles, the value of any given qubit should be a coin toss, unrelated to what you started with. Every trace of the original pattern should be gone. The second fact is the one that decides everything. The team ran the same experiment from a huge collection of different random starting arrangements. Not a handful, enough to sample the full space of possibilities, using a sampling trick that lets a modest number of runs stand in for an enormous number. The rhythm appeared every time. Sit with that for a second. The starting arrangement was random. The half-tempo response was not. Whatever configuration you handed the machine, it locked into the same beat, at the same rate, with the same stubbornness. That universality is the difference between a trick and a phase of matter. You can get almost any system to oscillate for a while, if you tune it perfectly and start it in exactly the right place. Push a wine glass at the correct pitch and it will ring. Nudge it wrong and it just sits there. That kind of behaviour is fragile, and fragile behaviour is a curiosity. Something that works from every starting point without tuning is a property of the material itself. Steel is hard whether you found it in a beam or a spoon. Salt is cubic whether it came from a mine or a sea. Those are phases, and phases do not care how you got there. The sycamore rhythm behaved like a phase. There was one more test, and it was the cruelest one. Because a skeptic could still argue that the machine had simply been set up too well, and that a slightly sloppier experiment would collapse. So the team started making mistakes on purpose. Deliberately breaking your own experiment sounds like sabotage. In this case, it was the entire point. The flipping pulse in each cycle is meant to turn every 0 into a 1 and every 1 into a 0. In the language of the field, that is a rotation of 180 degrees, perfect flip. The team stopped doing perfect flips. They tuned the pulse to 170 degrees, then 160, then further off. Each qubit now got a shove that fell short of a full turnover, leaving it in a mixed state somewhere between 0 and 1, carrying an error that should compound with every cycle. Follow the obvious logic and the outcome is clear. If your flip is 10 degrees short, then after 2 cycles you are 20 degrees off. After 10 cycles you are 100 degrees off, and long before you reach cycle 100 the rhythm should have wandered completely away from half-tempo. The beat should slide the way a drummer slides when their timing is slightly wrong, and the whole song comes apart 4 minutes later. The beat did not slide. The system kept answering at exactly half-tempo. The oscillation got a little weaker, the signal a little quieter, and the period stayed pinned to 2 cycles as if it had been welded there. Physicists call this rigidity, and it is the true fingerprint of the phase. Here is a way to picture what is happening. Imagine a choir of 100 people, and every single one of them is slightly off pitch, some sharp, some flat, nobody correct. You would expect the sound to be a mess. Instead, the singers hear each other, pull toward each other, and land together on one clean note that none of them was singing alone. The qubits do that with timing. Each one, on its own, is drifting. But they are talking to their neighbours, and those interactions punish anything that falls out of step. Errors that would ruin a lone qubit get absorbed by the group. The collective locks the tempo down. That is why the result counts as matter rather than engineering. A machine works because its parts were built precisely. A phase of matter works because its parts protect each other from imprecision. Steel does not become soft because one atom sits crookedly. A magnet does not lose north because a few of its atoms point the wrong way. Collective behaviour shrugs off individual failure, and that shrugging is what physicists mean when they call something a phase. The rigidity also killed the simplest skeptical explanations. Coincidence collapses under variation, and this survived it. Fine-tuning collapses under detuning, and this survived that too. But surviving 170 degrees is a long way from surviving forever, and the word forever was doing enormous work in every description of a time crystal. There was still a monster in the room. That flipping pulse pumps energy in on every cycle. The interaction step spreads it around. Every rule of thermodynamics says this system should be steadily heating toward chaos, and heat should have eaten the rhythm alive. Something in that chip was blocking the heat. And the mechanism doing the blocking is one of the strangest discoveries in modern physics, because it describes a material that refuses to let energy travel through itself at all. Drop a hot coal into a bathtub and the heat goes everywhere. That is what heat does. It spreads. Some quantum systems refuse. The mechanism is called many-body localization, and it arrived in physics as a genuine shock, because it describes a situation where energy dumped into one corner of a system stays in that corner essentially forever. No spreading, no sharing, no march towards sameness. The ingredient that makes it happen is disorder, and disorder means the parts are all slightly different from one another. In the Sycamore experiment, the team deliberately gave every qubit a slightly different interaction, strength with its neighbours, randomly chosen. No two links quite alike. That messiness was not a flaw in the hardware. They put it there on purpose, because messiness is the thing that stops the heat. Here is why it works. For energy to move from one qubit to the next, the two of them have to be compatible. They need to be tuned closely enough that a bit of energy can hop across without breaking any rules of quantum bookkeeping. When every qubit has a different personal frequency, that hop keeps failing. The energy arrives at the door, finds it does not fit, and stays where it was. Picture a city where every road has a different speed limit, chosen at random, and cars are forbidden from changing speed. A car doing 40 arrives at a street marked 23 and simply cannot enter. Another car doing 17 faces the same wall. Traffic never flows. Nothing reaches downtown. A crash on one corner never causes a jam 3 miles away, because there is no route from here to there. That is a localized system. The parts are all present, all interacting a little, and completely unable to share. Now bring back the flipping pulse. Every cycle it injects energy. In an ordinary system, that energy would distribute itself, raise the temperature, and drown the rhythm. In a localized system, the energy has nowhere to go. It cannot spread, so it cannot pile up into heat, so the system never climbs toward that scrambled infinite temperature ending. The rhythm survives because the heat is stuck in traffic. This is what made the Sycamore result different from every earlier attempt. Other groups had produced time crystal behavior before. Their versions relied on the heating being slow rather than blocked, which meant the rhythm was living on borrowed time. It looked eternal because nobody watched long enough for it to fail. Localization changes the promise from a long time to all time. The block is structural. Wait 1,000 years and the roads still do not connect. There is one more consequence, and it is the deepest one. In a localized system, every quantum state of the system carries the pattern, including the high-energy ones. Physicists call that eigenstate order. It means the ticking is written into the fabric of the thing rather than into one lucky starting configuration. That is what promotes a curiosity into a phase. Not everyone agreed the distinction mattered, and that disagreement turned into one of the sharpest rivalries in recent physics, fought between two groups who had each proposed time crystals and had very different ideas about what deserved the name. By 2021, two separate groups of theorists both had a claim on the discrete time crystal. One group included Vedika Khemani, Shivaji Sondhi, and Roderick Musner, who had worked out the localized version where disorder blocks the heat. The other included Norman Yau and Chetan Nayak, who came at it from a different direction and helped establish how you would recognize one in a real experiment. Both groups had published. Both had legitimate claims to the idea, and they disagreed in public about what counted. The disagreement had teeth because it decided which experiments were real. Yau and Nayak's side teamed up with Chris Monroe at the University of Maryland, who works with trapped ions rather than superconducting circuits. His machines hold individual charged atoms in place using electric fields, then poke them with lasers. Beautiful hardware. Completely different from a chip. That collaboration reported a time crystal made of trapped ions in the journal Science, and their version came with an asterisk. They called it pre-thermal. Pre-thermal means before the heating. The system holds its rhythm for a long stretch, behaving exactly like a time crystal in every measurement you could make. Then, eventually, the heat wins. The parts share energy after all, the rhythm decays, and the system slides into equilibrium the way the second law always insisted it would. How long is the stretch? Long enough that the experiment ends first. Long enough that if you only watch the data, you cannot tell the difference. The other camp found this unsatisfying, and their objection is worth understanding. A diamond and a puddle of water both have structure. The diamond keeps it indefinitely. The puddle keeps it until the sun comes up. If your definition of crystal covers the puddle, the word has stopped meaning much. Pre-thermal behavior in that view is a puddle. Impressive, useful, worth studying, and temporary. A true phase of matter should not have an expiration date buried in its mathematics. The pre-thermal camp pushed back with a fair argument of their own. Nothing lasts forever in a real laboratory. Every experiment sits inside a room, connected to wires, absorbing stray radiation. Even a localized system dies once the outside world reaches in. Demanding true permanence sets a bar no experiment can clear, which makes it a philosophical requirement rather than a scientific one. Both sides were making sense, which is what made the fight interesting rather than petty. The localized camp had hitched itself to Google's hardware precisely because that was where the argument could be settled. A processor gives you the disorder you need, the control you need, and the ability to measure every component separately, which set up the hardest problem in the entire story. The Sycamore experiment lasted well under 1/1000th of a second, about 100 cycles. Then the machine's own imperfections ate the signal, because roughly one operation in 100 goes wrong, and those failures accumulate. The team was claiming a phase that lasts forever, using a measurement that lasted less than a millisecond. To prove it, they had to find a way to separate the death of the phase from the death of the machine. Every quantum computer is a leaky bucket, and the Sycamore team decided to measure the leak. Here was their situation. The oscillation in the raw data faded away over roughly 100 cycles. Two completely different explanations could produce that fade. Explanation 1. The time crystal is temporary, the rhythm genuinely decays, and the physics itself is running out. Explanation 2. The time crystal is permanent and the hardware is falling apart around it. Those two look identical on a graph. Separating them took several clever moves at once. The first move was to characterize the machine's own failure rate independently, using circuits where the expected answer was already known. That gave the team a decay curve belonging purely to the hardware, a measure of how fast the bucket leaks regardless of what you pour in. The second move exploited something specific to their setup. Because the qubits are localized, each one behaves in a way that depends mostly on its own neighborhood rather than the whole array. That let the team compare small groups against large ones and check whether the rhythm weakened as the system grew. A temporary effect fades faster in a bigger system, because bigger means more routes for energy to escape. A true phase holds steady. The third move is the one that sounds like science fiction. They ran the circuit forward for a set number of cycles, then ran it backward, undoing every operation in reverse order. In a perfect machine, forward and back returns you exactly where you started. Any difference between the start and the finish is pure hardware error, cleanly separated from the physics. Time reversal is a diagnostic tool, the machine checking its own honesty. Put the three moves together and the picture came apart cleanly. The hardware decay accounted for the fade. Strip it away and the underlying oscillation showed no sign of weakening at all. There is one more piece, and it is the most elegant. To claim a phase of matter, you need to show the behavior holds across the whole space of possible starting states, and that space is astronomically large. 20 qubits have more than 1 million configurations. Testing them one at a time is hopeless. The team used a sampling method that lets a small number of specially chosen random states stand in for the entire collection, the way a well-designed poll of 1,000 people can predict a national election. The trick works because quantum systems have a property called typicality, where a random state carries information about the average behavior of all states. Their conclusion held across the board, so the claim survived. A phase of matter verified inside a machine that was falling apart the entire time, using errors as a measuring stick instead of an obstacle. And what they had made was genuinely new in a way that goes past the ticking. Every phase of matter in every textbook is defined at equilibrium. Ice is what water does when it settles at low temperature. Steam is what it does when it settles at high temperature. Settle is the operative word, and it appears in every definition. This thing never settles. It cannot exist at rest. Stop shaking it, and it stops being what it is. Which forced physicists to admit that their entire classification system for matter had been built with a blind spot in it. Ask what temperature a time crystal is, and the question falls apart in your hands. Temperature is a statement about a system that has settled down. It describes how energy is shared among the parts once the sharing has finished. Every part of a hot cup of coffee is hot. Every part of an ice cube is cold. That evenness is what lets one number describe the whole thing. A driven quantum system never finishes. Energy is arriving on every cycle. The system is permanently mid-process, and there is no settled distribution to summarize, so it has no temperature. None. The question has no answer, the way asking for the color of a sound has no answer. That is a genuine problem because temperature sits underneath almost everything in the standard picture of matter. Phase diagrams are maps with temperature on one axis. Melting points, boiling points, and freezing points are all temperatures. Take that axis away and the map is blank. Physicists had to build a new way of asking what makes something a phase. The answer they landed on is about persistence and shared behavior. A phase is a pattern that many parts fall into together, that survives small changes to the details, and that cannot be destroyed by nudging one component. Hardness, magnetism, and superconductivity all fit that description. So does the half-tempo rhythm. The old definition was a special case of the new one, which happens to hold when systems settle. It works beautifully for rocks. It simply never covered everything. And this opened a door that physicists are still walking through. If matter can organize itself in ways that only exist while energy flows, then the catalogue of possible phases just got enormously bigger. Every arrangement in your chemistry textbook is a settled arrangement. The unsettled ones were never listed because nobody could make them, study them, or in most cases imagine them. A hint of how big that space might be arrived in 2025, when a collaboration between a university in Munich, Princeton, and Google used 58 qubits to create a phase that had been predicted on paper and never once observed. They shook a two-dimensional array of qubits and produced a state with a kind of order that equilibrium thermodynamics flatly forbids. One of the researchers on that work summed up the shift. Quantum processors, she said, are more than computational devices. They are experimental platforms for discovering entirely new states of matter. That single sentence rearranges what a quantum computer is for. Still, a skeptic had one solid objection left, and it was the right objection to have. Everything so far happened inside superconducting circuits made by one company. Aluminum loops, microwave pulses, one specific fabrication process, one specific style of refrigerator. Any of those details could be producing an artifact that looks like physics and is actually engineering. Real phases of matter do not care what they are made of. Magnetism shows up in iron, in nickel, in rare earth alloys, in materials that have nothing in common except the right internal arrangement. That indifference to substrate is how you know you are looking at a law rather than a quirk. So the test was obvious. Find the same rhythm somewhere completely different. Somebody did, in one of the hardest materials on Earth, using flaws that a jeweler would throw away. A perfect diamond is boring. The interesting ones are broken. Take a diamond, which is nothing but carbon atoms locked in a rigid grid, and knock one carbon atom out. Then put a nitrogen atom in the space beside the hole. What you have made is a defect, an imperfection, the kind of thing that lowers the price of a gemstone. Physicists treat it as one of the finest quantum systems available. The combination of the missing atom and the nitrogen next to it is called a nitrogen vacancy center, and it behaves like a single artificial atom trapped inside solid carbon. It has quantum states you can set with light and read with light. And because the diamond around it is so rigid and so chemically boring, the defect stays quiet even at room temperature. protected by the fortress it sits inside. Around that defect sit other useful oddities. Ordinary carbon has 6 protons and 6 neutrons in its nucleus. About 1 carbon atom in 100 carries an extra neutron, and that extra neutron gives the nucleus a magnetic property that the defect can talk to. So a team at a research institute in the Netherlands built a system out of those nuclei, 9 of them addressed through a single nitrogen vacancy center, controlled with microwave pulses and laser light. Then they ran a driven experiment and looked for a subharmonic response. They found one. A rhythm at half the driving tempo, robust against imperfect pulses, appearing in a lump of crystal at conditions no superconducting chip could survive. Their results went up in the summer of 2021, at almost the same time as the superconducting work, discovered independently by people using entirely different equipment. 2 platforms with nothing in common. Aluminum loops chilled to 1/100th of a degree above absolute zero, and carbon nuclei inside a gemstone. Different materials, different control methods, different temperatures, different countries, same rhythm. That near collision is exactly what physicists want to see, because independent confirmation with different hardware removes the possibility that one machine was fooling one team. Trapped ions had already shown related behavior. Cold atoms would follow. Later work found time crystal behavior in other systems entirely, until the effect stopped looking exotic and started looking like a category of thing that matter does when you shake it correctly. A researcher on the Diamond Project made one honest observation about all of it. A perfectly isolated time crystal could in principle live forever, and any real experiment eventually decays through contact with its surroundings. Extending that lifetime, he said, is the next frontier. So the phase is real, and the objects we build to hold it are mortal. Both statements are true at once, and physicists are comfortable with that, the same way a mathematician is comfortable saying a perfect circle exists, while every drawn circle is slightly wrong. Which leaves the question that everybody outside physics asks the moment they hear about a thing that ticks forever. If it never stops and nothing is winding it, then surely somebody can plug something into it. The answer is more interesting than a flat refusal. People have been trying to build machines that run on nothing since at least the 12th century, and every single one has failed. The catalogue of attempts is genuinely charming. Wheels with weighted arms designed to always be heavier on one side. Water that pumps itself uphill so it can fall again. Magnets arranged to pull a ball forever around a track. Some of these were sold to investors. A few were patented. None worked, because each one quietly ignored friction or air or the energy it took to lift something in the first place. So when a physicist says a time crystal ticks forever, the alarm should go off. Here is the accounting done properly, the drive is doing work, every cycle that microwave pulse arrives, and generating it takes electricity from the wall. The refrigerator keeping the chip cold consumes serious power, enough to run a small household appliance continuously. Nothing about the setup is free, and nobody involved claims otherwise. The remarkable part is what the qubits do with the energy. Ordinarily, a driven system absorbs the energy you feed it. That is what heating means. The energy goes in and stays in, raising the temperature until the system reaches its scrambled ending. Every pulse makes the system a little hotter than before. The localized system takes the energy and gives it back. It absorbs during part of the cycle and releases during another, ending each cycle roughly where it started. No net accumulation. The energy passes through rather than piling up. Picture a swing again. When you push a swing, you add energy on the way, and the swing gives most of it back as it comes toward you. A well-timed push keeps the arc the same size. It never climbs higher and never collapses. The swing is doing something forever, and you're still doing the pushing. That is why nobody can plug anything into a time crystal. To extract useful work from a system, you need to take energy out of it, and end up with the system in a lower energy state than before. Every engine ever built runs on that principle, moving energy from somewhere hot to somewhere cold and taking a cut on the way through. A time crystal has nothing to give. It returns to the same state on every cycle, holding no surplus. Reach in and take energy and you break the very balance that lets the rhythm exist. The moment you draw power, the crystal stops being a crystal, so the second law survives intact. What is unusual here is the refusal to heat, and refusing to heat is not the same thing as creating energy. The clearest way to say it is this. A time crystal is the world's most useless perpetual motion machine. It moves forever, and it will never turn a single wheel. That still leaves the other half of thermodynamics unaccounted for. Energy is one law, entropy is a separate one, and entropy is the law that says organized things must become disorganized. A system that holds a pattern indefinitely, across every starting state, looks like a system refusing to become disorganized. Something has to give, and what gives is one of the most counterintuitive ideas in quantum physics. Entropy climbs because systems explore. That is the piece most explanations leave out. The reason a shuffled deck stays shuffled is that shuffling wanders through the enormous space of possible orderings, and almost all of them look random. The reason milk mixes into coffee is that the molecules wander through the enormous space of possible positions, and almost all of them are mixed. Wandering is the engine. Cut off the wandering and the climb stops. That is exactly what localization does. In an ordinary quantum system with many parts, any starting configuration can eventually reach any other configuration. There are pathways connecting everything to everything. Given enough time, the system tours its own possibilities, and since the scrambled possibilities vastly outnumber the neat ones, it spends nearly all its time scrambled. In a localized system, the pathways are broken. Most configurations simply cannot be reached from where you are. The system has enormous numbers of possible states available on paper, and the overwhelming majority are walled off from each other, unreachable no matter how long you wait. Imagine a library the size of a city, with millions of books in millions of rooms, and no corridors between the rooms. Every book that starts in room 400 stays in room 400 forever. You could describe that library as containing millions of possible arrangements, and none of those arrangements can ever be produced because nothing can move. That library never becomes disordered. Its books never mix, and no law of physics has been broken because entropy climbs through exploration, and there is no exploring to be done. The information about where you started stays exactly where you left it. That is the technical heart of the whole phenomenon. A localized system remembers its initial conditions indefinitely, and that memory is what carries the rhythm cycle after cycle. Normal matter forgets. Drop a coin in a bucket of water and stir it, and within seconds the water has no record of where the coin entered. The swirls die. The information smears out into unmeasurable heat. A localized system holds on. Poke qubit number 7, and the trace of that poke is still detectable at qubit number 7 later, unblurred, undelivered to its neighbors. Physicists spent decades assuming this was impossible for interacting systems. Interaction was supposed to guarantee mixing. Localization proved that disorder, of all things, can preserve order, because randomness in the connections prevents information from flowing along them. That is the reversal that made the field sit up. Mess up your system enough, and it becomes incapable of getting any messier. Once that idea was established, an obvious question followed. If disorder can block thermalization, what else can? Because localization requires deliberate randomness, engineered in. Nature rarely provides it in exactly the right form. The recipe is powerful and it is fussy. Physicists began hunting for systems that refuse to thermalize for entirely different reasons. Systems that are clean and orderly and still somehow decline to forget. And in a laboratory in Massachusetts, a machine built out of 51 individual atoms held in place by laser light had already done something nobody had asked it to do, and nobody could explain. The atoms were supposed to scramble in a few millionths of a second. They kept returning to the start instead, over and over, like a song stuck on a loop. The machine was a quantum simulator built from individual rubidium atoms, each one grabbed out of a gas and pinned in place by a tightly focused beam of laser light. 51 of them, arranged in a neat line spaced a few millionths of a meter apart. Every atom held still, addressable, and readable. Then the team pumped energy into the atoms, pushing their outermost electron into an orbit enormously larger than normal. An atom in that puffed-up condition is called a Rydberg atom, and it is a genuine oddity. Its electron can sit 1,000 times further from the nucleus than usual, turning an object smaller than a nanometer into something you could almost see with a good microscope. Blowing up an atom that way has a dramatic side effect. its electric influence stretches out and starts shoving its neighbours around. Specifically, one puffed up atom forbids the atoms beside it from puffing up too. There is only room for one. Physicists call this the blockade, and it turns a line of independent atoms into a tightly connected chain where every atom's options depend on its neighbours. The team set up a starting arrangement where every other atom was excited, ordinary, excited, ordinary, all the way down the row. A pattern with a repeating unit of 2, which is a perfectly reasonable thing to build and a completely unreasonable thing to expect to survive. Because this system was clean. No deliberate randomness, no disorder blocking the pathways, every atom identical, every gap identical. According to everything in the previous chapters, this is a textbook recipe for fast thermalization. The pattern should dissolve within a few interaction times and never be seen again. It dissolved. Then it came back. The measurements showed the atoms losing their arrangement, sliding toward disorder, and then reassembling into something close to the original pattern. Then losing it again, then reassembling again. Persistent oscillations, running far longer than any reasonable estimate said they should, in a system with nothing obvious protecting them. The team ran it from other starting arrangements to see how general the effect was. Those other arrangements did exactly what theory predicted. They scrambled, they thermalized, they died. The alternating pattern was special, and nobody had predicted that it would be. This is a different flavour of strangeness from the time crystal. There, disorder walled off the whole system, and everything was protected. Here, almost the entire system thermalized on schedule, obediently, and a narrow slice of it refused. One rebel corner inside an otherwise law-abiding machine. Theorists gave the effect a name borrowed from an older piece of physics. They called them quantum many-body scars, after a phenomenon where certain paths get burned into a chaotic system and stay visible when everything around them has smeared out. The name is evocative. The consequences were far worse than evocative. Because the assumption those 51 atoms had just violated is not a small technical rule tucked away in a specialist journal. It is the bridge connecting quantum mechanics to the entire science of heat, temperature, and everyday matter. And it has a name that physicists say with real respect. Physics has a hole in it, right at the join between the very small and the everyday, and for most of a century nobody could fill it. The problem is this. Every equation in quantum mechanics runs just as well backwards as forwards. Film two particles colliding and play the reel in reverse, and nothing in the footage breaks a single rule. At the level of individual quantum objects, the universe has no preferred direction, no past, no future, no arrow. Then you zoom out and the arrow is everywhere. Coffee cools, ice melts, nothing unbreaks. So where does one-way behaviour come from, if the underlying rules point both ways? The answer arrived in two pieces, published 3 years apart by two physicists who did not know they were working on the same question. What they proposed is called the eigenstate thermalization hypothesis, and it is the most important idea in this story that almost nobody outside physics has heard of. Start with the setup. Any quantum system made of many parts has a huge collection of possible energy states. For a chain of 51 atoms, the number of possible configurations runs past 2 quadrillion. Each one of those is a valid arrangement the system could occupy. The old assumption was that a single state, on its own, has nothing to do with temperature. Temperature was supposed to be a statistical thing, an average over enormous crowds of states, meaningless for one on its own. The hypothesis says something far bolder. Take any single one of those states, chosen at random from the middle of the pile. Ignore the whole system and look only at a small piece of it. 3 atoms out of 51. What you will find written into that fragment is temperature, pressure, every thermal property of the whole. Think of a hologram. Cut a holographic plate in half, and you still get the full image from each piece, a little blurrier. The whole is written into every part. Once you accept that, the arrow of time falls out for free. Start your system however you like, in whatever exotic combination of states appeals to you. As it evolves, the different pieces of that combination drift out of step with each other, and their contributions cancel. What survives is the average, and every state in the average already carries the same thermal answer. So the system looks like it has reached equilibrium, because from the point of view of any small measurement, it has. The information about where you started is still there in the full quantum state, spread across every part and impossible to gather back up. That is the bridge. It connects reversible microscopic law to irreversible everyday experience, and virtually all of modern statistical physics is built on top of it. Now look at what those 51 atoms did. They oscillated. From that one starting arrangement, local measurements refused to give thermal answers, and they kept refusing long past the point where the hypothesis says all memory should be gone. So somewhere in that pile of 2 quadrillion states, a small set of them must be different. States that carry no thermal information in their fragments, states where the hologram trick fails. Theorists went looking and they found them. A tower of evenly spaced states, hiding inside the chaos, numbering perhaps a few dozen out of quadrillions. That is a vanishing fraction. It is also enough to break something because the hypothesis had been stated for all states, and all is a word with no room in it. The next question was how those rare states managed to hide, and the answer turned out to involve the geometry of a space so large that the universe cannot contain a map of it. Try to picture the space of possibilities for a modest quantum computer, and your imagination gives out almost immediately. 10 qubits have 1,024 possible configurations. 20 qubits have just over 1 million. 50 qubits pass a quadrillion. Keep going and something absurd happens. At around 266 qubits, the number of possible configurations exceeds the number of atoms in the observable universe. Physicists call this collection of possibilities Hilbert space, and the point worth holding on to is that a quantum system does not sit at one point in that space. It spreads across it, and its behavior depends on which regions it can reach. Thermalization is a statement about reach. A system thermalizes because it can wander, and because the overwhelming majority of destinations look scrambled. 2 chapters ago, disorder cut the roads. That was localization, and it required deliberate randomness engineered into the hardware. There is another way to cut roads, and it needs no randomness at all. It happens when the rules of the system forbid certain moves. Go back to those puffed up atoms in the laser trap. The blockade means no 2 neighbours can be excited at the same time. That single restriction rules out enormous swathes of Hilbert space instantly. Any arrangement with 2 excited neighbours is simply unreachable, forever, because there is no legal move that produces one. Restrictions like that can slice the space of possibilities into pieces that never communicate. Physicists call the effect fragmentation, and the number of disconnected pieces can grow exponentially with the size of the system. Think of a board game where pieces move only diagonally. Half the squares on the board are permanently unreachable from any given starting square, and no amount of play will ever put a piece there. The squares exist. The rules make them unreachable. A fragmented quantum system lives inside one of those sealed regions. It can explore that region thoroughly, thermalize inside it, and reach a kind of local equilibrium. And it will never know that the rest of the space exists. That produces behavior that looks like memory. The system remembers which sector it started in because leaving is impossible. Scars sit somewhere between fragmentation and ordinary chaos, and the details are still argued over in the literature. What matters is the shape of the discovery. Physicists went looking for exceptions to thermalization and expected to find one narrow, fragile loophole. They found a family. Disorder blocks the roads. Constraints delete them. Periodic driving builds new ones. Each mechanism produces systems that refuse to forget, for entirely different reasons, and each one was invisible until machines existed that could hold a quantum system still enough to look. Which reframes the last 20 years of this field. Nobody set out to overturn statistical mechanics. Engineers set out to build a computer, and the process of building it produced a laboratory, more controllable than anything physics had ever owned. That laboratory started returning results that theory had not asked for. By 2025, one of those results arrived with a claim attached that goes further than anything so far. A collaboration announced they had made a phase of matter that equilibrium thermodynamics does more than fail to describe. It forbids it outright. Stop the drive and the material vanishes. That is the first strange thing about what 58 qubits produced in 2025. The work came from a collaboration between the Technical University of Munich, Princeton, and Google Quantum AI, published in Nature in September of that year. They set out to build something that had lived on paper since a theory proposal years earlier, and had never once been assembled. They called it a Floquet topologically ordered state. Break that name into parts and it becomes manageable. Floquet you have already met. It means periodically driven, shaken with a steady rhythm, the same setup that produced the time crystal. Topological order is the piece that deserves attention because it describes a kind of organization that no microscope can see. Every phase of matter in an ordinary textbook is defined by something local. Ice is ordered because atoms sit in a repeating grid, and you could confirm that by examining one small patch. A magnet is ordered because its atoms point the same way, and again, one patch tells you. Zoom in far enough and the order is visible right there in front of you. Topological order hides from that test completely. Examine any small patch of a topologically ordered material, and you will find nothing. No pattern, no alignment, no structure of any kind. The patch looks like featureless noise. The order lives in the relationships between distant parts. It is written in how the whole system is knitted together, and it exists only at the scale of the entire object. Here is a way to picture it. Take a long strip of paper, give it a half twist, and tape the ends together. You have made a loop with one side instead of two. Now hand someone a tiny piece of that loop under a magnifying glass. They will see flat paper, exactly like flat paper anywhere. The twist is real, it changes everything about the object, and it is invisible in every fragment. Topological order works like that twist, carried by quantum entanglement rather than paper. Materials with this property are rare and precious, because information stored in the twist is very hard to destroy. Local noise damages local things, and there is nothing local to damage. Now put the two halves of the name together, and the reason this experiment mattered comes into focus. Equilibrium thermodynamics has a catalogue of the topological orders that are allowed to exist in a settled material. The catalogue has limits, and certain arrangements are ruled out by the mathematics. Driving the system escapes the catalogue. Shaking generates patterns of order that the settled rules forbid, and the researchers built one of the forbidden ones, which brings back the opening problem. This phase cannot be bottled, it has no existence at rest. Stop the drive for a fraction of a second and the entanglement that carries the order unravels, and you're left with 58 ordinary qubits doing nothing interesting. Matter that exist only as a process. To prove they had really made it, the team needed to see one of its signatures directly, and the most dramatic one runs around the outside edge of the system, like water circling a drain that never empties. Around the rim of that qubit array, something started moving in a single direction and would not turn back. Physicists call these chiral edge modes, and chiral is a word borrowed from chemistry meaning handed. Your left hand and your right hand are mirror images that cannot be laid on top of each other. Chiral things have a built-in preference for one direction over its reflection. An edge mode is a disturbance that travels along the boundary of a material while the inside stays quiet. The interior can be completely inert, unable to conduct anything, and the border alone carries the traffic. What makes the chiral version astonishing is that the traffic is one way, not mostly one way, entirely. There is no channel available for anything to travel the other direction, and physics does not permit one to be created. The team watched this directly. They set up their driven array, disturbed one region of the boundary, and imaged what happened next. The disturbance walked around the perimeter, always the same way around, cycle after cycle. Now consider what that means for reliability. Every river you have ever seen has eddies. Water hits a rock and part of it swirls backward. That backward motion is where energy gets lost and patterns fall apart, and it is why signals in ordinary conductors degrade. A one-way channel cannot have eddies, because backward is not an available direction. Put an obstacle in the path, and the disturbance simply goes around it and continues, carrying the same information it started with. Add a defect, roughen the edge, remove a few qubits from the boundary. The flow continues. This is the practical payoff of topological protection, and it is why so much money is chasing these phases. Information carried in a channel with no reverse gear is extraordinarily difficult to corrupt. There is a version of this in ordinary materials, discovered in the 1980s, where electrons confined to a flat sheet under a strong magnetic field produce edge currents so precise that the measurement became a standard for defining electrical resistance worldwide. The precision reaches roughly 1 part in a billion, which is the kind of number metrologists dream about. The driven version on a chip has something the older version lacks: programmability. You choose the shape of the boundary, the strength of the coupling, the tempo of the drive, and you can watch what happens when you change any of them. And the team used that control to look at the one place nobody could look before: the interior. An edge current tells you a phase exists. The interesting physics lives in the middle, where the material is supposedly doing nothing at all. In a topologically ordered system, that quiet middle can hold disturbances of its own, and those disturbances behave like objects. They move, they can be created and destroyed in pairs, they carry properties. And when physicists worked out what kind of object they must be, the answer broke a rule that had been taught as absolute since the 1920s. Everything in the universe is one of 2 kinds of thing. These are a third. For 100 years, every particle ever found has belonged to one of 2 families, and nobody has ever found an exception. The first family is the fermions: protons, neutrons, electrons, quarks, everything you would call stuff. Fermions are antisocial. 2 identical ones refuse to occupy the same state, and that refusal is why matter takes up space. Push your hand against a table, and the reason it stops is fermions declining to share. The second family is the bosons, photons of light, the particles that carry the strong force, the famous Higgs. Bosons are gregarious. They pile into the same state happily, which is why you can shine 1,000,000 laser photons down one identical path. 2 families. That is the whole list. The division comes from a piece of mathematics about what happens when you swap 2 identical particles. Swap 2 bosons and the description of the system stays exactly as it was. Swap 2 fermions and the description picks up a minus sign, a flip that produces all that antisocial behavior. Those are the only 2 options, and the proof of that is airtight. In 3 dimensions. The proof leans on a fact about the shape of space that is so ordinary you have never thought about it. In 3 dimensions, when you swap 2 particles by moving one around the other, the path you took can always be untangled. Lift it, twist it, and the loop shrinks away to nothing. Since the path leaves no trace, only the final swap matters, and swapping twice must return you to the start. That constraint leaves exactly 2 possibilities. Flatten the world to 2 dimensions and the argument dies. On a flat plane, a loop around another object cannot be lifted out and shrunk away. There is no up to lift it into. The loop is stuck, and going around clockwise is permanently different from going around the other way. Which means, in 2 dimensions, the path is part of the answer. Once path matters, the swap is free to do something other than nothing and something other than a minus sign. It can produce any twist at all, anywhere between the 2 old options. Physicists name these things anyons because the swap can produce any phase, and the name has a joke buried in it. Nothing fundamental in our universe is an anyone, because our universe has 3 spatial dimensions and the old proof holds. So they appear another way. An anyon is a quasi-particle, which means a disturbance in a material that behaves so much like a particle that treating it as one is the sensible thing to do. Think of a ripple crossing a pond. The ripple has a position, a speed, and it can bounce off things. It is also made of nothing but water doing something interesting. Confine electrons to a flat sheet, get them cold enough and correlated enough, and the ripples in that sheet can be anyons. Some carry a fraction of an electron's charge, which sounds impossible until you remember that 1/3 of a wave is a perfectly sensible object. Anyons come in flavours, and one flavour is far stranger than the rest. Because for those, swapping 2 of them does more than twist the description. It rewrites it, and the system never forgets what you did. Move 2 of these objects around each other, and the material remembers the choreography forever. The tame flavour of anyone is called abelian, after a 19th century mathematician, and the important feature is that order does not matter. Swap object 1 with object 2, then 2 with 3, and you get the same result as doing it the other way round. Each swap adds a twist, the twists accumulate, and the bookkeeping stays simple. The wild flavour is non-abelian, and there, order changes everything. A collection of non-abelian anyons has multiple distinct quantum states available to it, even when every anyon is sitting perfectly still in the same place. The states are indistinguishable by any local measurement. Look at each anyone individually, and they are identical. The difference lives in the history of how they were moved. Swap two of them, and the whole system shifts from one of those hidden states into another. Do the swaps in a different sequence, and you land somewhere else. The material has recorded the sequence of your moves permanently in a form that no local disturbance can erase. Picture a magician with 3 cups and a ball hidden under one. As the cups slide around each other, the ball's location changes, and where it ends up depends entirely on the order of the moves. Watching any single cup tells you nothing at all. The information is in the choreography. Physicists call the moves braiding, and the name is exact. Draw the paths of the anyons through time and you get a braid, like hair or rope, with strands crossing over and under one another. 2 braids give the same result only when you can deform one into the other without cutting any strand. A knot is a knot, and no amount of jiggling makes it something else. Which is why people who build quantum computers get excited. Information stored in a braid is protected by geometry. Every other kind of qubit fails when its environment nudges it, and those nudges are relentless. Braided information ignores nudges entirely because a small vibration cannot untie a knot. To damage the stored information, the environment would need to pick up an anyone, carry it all the way around another one, and put it back. Random noise does not do that. The dream that follows is a machine where computation happens by moving quasi-particles around each other in patterns, and where errors are prevented by the shape of the movement rather than corrected afterwards. No error correction overhead. No armies of extra qubits standing by to fix mistakes. The obstacle was always the material. Non-abelian order has been suspected in certain exotic conditions inside semiconductors chilled near absolute zero under enormous magnetic fields, in states so delicate that decades of work has produced arguments rather than agreement. The candidates are real. Confirming them has been brutal. So a group of theorists asked a different question. Instead of hunting for a material that naturally hosts these things, why not build a system that hosts them on purpose? The answer required a machine that could measure part of a quantum system without destroying the rest, then use those measurements as a construction tool. In 2023, a company in Colorado switched on hardware that could do exactly that, and the phase of matter they made was assembled out of 27 charged atoms and a series of carefully chosen questions. The strangest part of the recipe is that measuring the system was the thing that created it. The machine was a trapped ion processor called H2, built by a company named Quantinuum. Its qubits are individual charged atoms suspended in electric fields inside a vacuum chamber, moved around by changing the fields and manipulated with lasers. Trapped ion machines are slower than superconducting chips and considerably more accurate, and they can perform one trick that mattered enormously here. They can measure a single qubit in the middle of a calculation, read the answer, and keep going with everything else intact. That capability is what made the experiment possible, and the reason traces back to a proposal from theorists at Harvard and Caltech, who had been searching for the shortest possible route to non-abelian order. Their insight ran against instinct. Measurement is normally the enemy in quantum computing. Looking at a quantum system collapses it and destroys the delicate superpositions you spent your whole circuit building. Every practical guide tells you to measure last. The proposal said to measure in the middle, deliberately, and to use the collapse as a construction step. Here is the shape of it. Prepare the ions in a state with the right ingredients present but scrambled together. Then ask a specific set of questions by measuring particular combinations of qubits. Each answer collapses part of the system, and each collapse rules out possibilities. Follow the answers with a short round of corrections, and the system falls into the state you wanted. The team called it a shortcut, and the mathematics behind why it works is genuinely lovely. Building this kind of long-range entanglement by ordinary means would take a circuit whose depth grows with the size of the system. Measurement collapses the whole array at once, so the cost stops growing. 27 ions. A handful of measurement rounds, a phase of matter that had never existed anywhere. Then came the proof. Making the state is one thing. Showing it is genuinely non-abelian requires demonstrating that the anyons remember choreography. So the team created pairs of anyons, moved them around each other in specific sequences, and measured what happened to the hidden states. Different braids gave different answers. The order of operations changed the outcome. That is the signature, and it cannot be produced by anything abelian. They published in Nature in early 2024, and the reaction from theorists was close to delight. One of the physicists behind the proposal pointed out that they had realized a new phase of matter and demonstrated its potential for computing in the same experiment. Google's superconducting hardware got there by a different route around the same time, braiding defects in a lattice of qubits and showing the same non-abelian behavior on a chip. Two platforms again, same physics. And in the driven system from Munich and Princeton, the anyons did something that pushed even this into strange territory. They stopped being the kind of anyon they started as. Halfway through the drive cycle, the excitations in that 58-qubit array were no longer the same species of thing they had been at the start. Physicists call it transmutation, and the word is deliberately chosen. It is the term alchemists used for turning one substance into another, and for once it fits. Here is what makes it possible. In a settled material, an anyon has a fixed type. It carries particular properties, it braids in a particular way, and those facts are permanent features of the phase it lives in. A material with one kind of anyon keeps that kind. Driving the system removes the permanence. The rules governing the excitation shift as the drive proceeds, and an object that was one type at the start of a cycle can find itself a different type by the end. Imagine a chess piece that becomes a knight while it is moving and a bishop when it stops. Everything about how it interacts with the board changes depending on where you are in the rhythm. Detecting that is a serious problem, because none of this is visible locally. Look at any patch of the array and you see qubits with no obvious structure. The type of an anyon lives in how it relates to everything else. The team built an interferometric algorithm to get at it. Interference is the trick underneath most quantum measurement. Split something into two paths, send it around, bring the paths back together, and look at how they add up. Where the paths agree, you get reinforcement. Where they disagree, you get cancellation. The pattern reveals differences too small to measure any other way. Applied here, the method let them measure a bulk topological invariant, which is a single number describing the twist in the entire system. Invariants of this kind cannot change gradually. They sit at one value, and any change is a jump. Watching that number and seeing it jump is how you catch a phase transforming. The measurements scale to 58 qubits, which for this kind of experiment is enormous, because the classical difficulty of checking the answer grows explosively with size. Simulating a highly entangled driven system of that size on a conventional computer is close to hopeless, which is precisely why the quantum processor was the instrument rather than the subject. Step back from the details and notice what has happened across the last several chapters. A machine sold as a calculator has produced a rhythm that thermodynamics forbids, a state of matter that only exists in motion, a current with no reverse gear, objects that belong to neither of the two families the universe is supposed to contain, and now those objects changing type in real time. None of it was on the roadmap. All of it came from people treating the hardware as a laboratory. There is one more pattern in these machines, and it is the one nobody wanted to find. It shows up as failure. Whole regions of a chip losing their quantum states at the same instant, in a way that error correction was built on the assumption could not happen. And the source of it turned out to be sitting several miles above the roof of the building. Quantum error correction rests on one assumption, and for years nobody checked whether it was true. The assumption is independence. Errors are supposed to strike at random, one qubit at a time, uncorrelated with each other. Given that, the fix is elegant. Spread one unit of protected information across many physical qubits, measure the relationships between them constantly, and use those measurements to spot and repair damage without ever looking at the information itself. The mathematics is beautiful and it works. Google demonstrated in 2024 that scaling up an array of qubits from a grid of 3x3 to 5x5 to 7x7 cut the error rate roughly in half at each step. More qubits, fewer errors, which is the crossing point the whole field had been chasing for nearly 30 years. Independence is what makes that possible. Random damage in scattered places is repairable, the way a few typos in a long document are repairable, when you have 3 copies to compare. Correlated damage is a different animal. If a single event wipes out half your qubits at once, every copy is damaged in the same place, and no amount of comparison recovers anything. Researchers at the University of Wisconsin found the correlations first. They were studying how the electrical charge state of qubits drifts over time, expecting each qubit to wander independently. The data said otherwise. The fluctuations were highly correlated, with qubits across the chip shifting together in lockstep. Something was reaching in and touching all of them at once. Follow-up work at Google found the same thing in a more violent form. Entire arrays would suffer what the team called catastrophic error bursts, where large numbers of qubits lost their quantum states simultaneously and stayed useless for a stretch before recovering. The recovery time is the detail that gave the game away. These were not permanent faults or manufacturing defects. Something struck the chip, caused chaos, and then faded. Physicists worked out the mechanism reasonably quickly. Superconductivity depends on electrons pairing up, and those pairs can be split apart by an energy deposit. The broken pieces are called quasi-particles, and they poison superconducting circuits, ruining the delicate conditions that qubits need. An energy deposit anywhere in the silicon base of a chip creates a burst of these things, and they spread through the substrate as vibrations, reaching qubits millimeters away. So one impact anywhere kills everything nearby. That reframed the entire error correction effort. All those elegant proofs assumed a world where this does not happen and the world does not cooperate. Which left one question standing, and it was the practical one. Something was hitting these chips regularly enough to matter, inside a sealed vacuum chamber, inside a refrigerator colder than deep space, inside a shielded room. To find out what, physicists did something no computer engineer would ever think to do. They bolted particle detectors inside the fridge. The instruments went in beside the chip, in the coldest part of the machine, pointed at nothing in particular. A group working with hardware at the Massachusetts Institute of Technology set up the cleanest version of the experiment. Their chip was small, about 5 millimeters on a side, and 1/3 of a millimeter thick, roughly the size of a sesame seed. 10 qubits sat spread across it. Above and below that chip they placed cosmic ray detectors, the kind particle physicists use, watching for charged particles passing through. Then they ran both systems at once and looked for coincidences. Every time a detector registered a particle, they checked whether the qubits had a bad moment at the same instant. A separate team in China ran a complementary version on a 63-qubit processor with 2 muon detectors inside the dilution refrigerator, tracking a different signature of the damage. Both experiments needed extraordinary timing. A quasi-particle burst lasts a fraction of a second, and the coincidence has to be tight enough that nobody can argue it was chance. They got their coincidences. The results answered the question and then went further, because the numbers revealed something about what these chips are. Essentially, every cosmic ray that hit the chip produced a response in the qubits. Not some, not most. The rate of qubit disturbances matched the independently measured rate of particles arriving, which means the array was catching almost everything that passed through it. That is the performance of a working particle detector. Think about what these devices are made of. A superconducting qubit is disturbed by an energy deposit far smaller than anything a conventional detector notices, because the whole design depends on being sensitive to the tiniest possible disturbances. Engineers spent decades making qubits fragile on purpose, since a system that can be nudged by a single microwave photon is a system that can be controlled precisely. Fragility is the feature. Sensitivity to almost nothing is the point, which means a quantum processor is, by accident, one of the most sensitive energy detectors ever constructed, and every cosmic ray that crosses it leaves a signature. The Chinese team pushed further and separated the sources. They compared the timing of quasi-particle bursts against their muon detectors and split the events into 2 categories, one from muons arriving from above and one from something else entirely. The something else turned out to account for the large majority. And the reason is a fact about the world that most people find deeply uncomfortable once they hear it. The building the quantum computer sits in is radioactive. Somewhere above your head, right now, a particle born in a dying star is passing through the roof. Cosmic rays are mostly protons, accelerated to enormous speeds by supernovae and other violent events across the galaxy, travelling for thousands of years before reaching us. When one strikes the upper atmosphere, it shatters, producing a shower of secondary particles that rain down over a wide area. The survivors that reach the ground are mostly muons. A muon is a heavier cousin of the electron, and it is astonishingly good at getting through things. Muons pass through concrete, through steel, through the ground itself. Roughly one crosses through your body every second, and you have never noticed a single one. The MIT team measured how much of the damage came from that source. Cosmic rays accounted for about 17% of the correlated error events on their chip, which means the other 83% came from closer to home. Everything around us is faintly radioactive. Concrete contains traces of uranium and thorium from the rock it was made of. Steel carries trace contamination. The copper and aluminum inside the refrigerator have their own tiny burden. Even the lead used for shielding, unless it has been sitting underwater for centuries, contains a radioactive isotope of its own. The Chinese team put numbers on it. Over 80% of the quasi-particle bursts they saw traced to gamma rays from the surroundings, with the remainder from cosmic ray muons. So the environment is glowing gently, all the time, and it always has been. Nobody noticed because nothing we ever built was delicate enough to care. Physicists have tried the obvious countermeasures. Lead shielding reduces the local radiation and does cut qubit decay rates. Moving the whole experiment underground helps more, because rock blocks a large fraction of the cosmic ray flux, and groups have run superconducting circuits in tunnels beneath mountains and seen the burst rate fall. Neither fixes it. Shielding stops gamma rays and does very little against a muon that has already crossed several miles of atmosphere. Going underground stops muons and does nothing about the radioactivity of the walls you built down there. You cannot outrun the sky and you cannot outrun the ground. So the engineering shifted. If the impacts cannot be prevented, the chip must be made to survive them. The most promising idea was called gap engineering. It works by tuning the materials in the circuit so that quasi-particles created in the silicon get trapped before they reach the sensitive parts. Build an energy barrier and the damage stays outside. Google tried it. The technique did reduce the catastrophic bursts, and for a while it looked like the problem was solved. Then they ran their error correction experiments and hit a wall. The logical error rate stopped improving. Below a certain point, the system simply refused to get better, and nobody could say why. The answer arrived in 2026, and it showed that the armor had worked exactly as designed while missing the real attack completely. The bursts were gone from the data, and the errors were still there, which is the sort of result that keeps engineers awake. The investigation was published in Physical Review X in 2026, and what the team found was a second, quieter failure mode that gap engineering had never been designed to catch. The original problem was destruction. A particle strike created quasiparticles. Those quasiparticles reached the qubits, and the qubits lost their energy states outright. Gap engineering blocked that pathway, and the catastrophic burst became rare. The new problem is desynchronization. Every superconducting qubit has a natural frequency, and controlling it means firing microwave pulses tuned precisely to that frequency. Get the tuning right, and the qubit responds exactly as instructed. Drift away from it and the pulses start missing. What the team discovered is that a radiation impact shifts qubit frequencies by as much as 3 MHz, which is 3 million cycles per second. That number sounds large, and in this context it is small, which is exactly what makes it dangerous. It is a shift of a tiny fraction of a percent. Nothing about the qubit is destroyed. It is still there, still holding a quantum state, still capable of doing everything it could do before. And it is now answering to a slightly different pitch than the one the control system is singing. Picture an orchestra where one instrument goes fractionally sharp. Nobody drops out. Every player is still playing every note. The sound turns to mush anyway, because being close is worthless when the whole point is matching exactly. Errors of this kind are called phase errors, and they corrupt the delicate timing relationships that carry quantum information. They also arrive correlated across many qubits at once, since a single impact shifts everything in the neighborhood together. That is the flaw Google kept hitting. A steady rain of tiny frequency shifts, invisible to systems watching for catastrophic destruction, quietly capping how good the machine could get. The finding lands hard, because it says the environment attacks in more ways than anyone catalogued, and building a truly fault-tolerant machine means understanding every one of them. There is a bright side, and it is the kind of turn that happens repeatedly in the history of instruments. Something that ruins your experiment is a signal, and a signal you can characterize as a measurement. The Chinese team said so directly in their paper. The technique they developed for monitoring simultaneous charge parity jumps across many qubits, built purely as a diagnostic for their own errors, has extremely high sensitivity to energy deposits. They listed what it might be used to detect: cosmic ray particles, far infrared photons, and low-mass dark matter. Most of the universe is made of something nobody has ever detected, and quantum processors may be accidentally good at looking for it. The evidence for dark matter is overwhelming and entirely indirect. Galaxies spin far too fast for the visible material inside them to hold together, and they should have flung themselves apart long ago. Clusters of galaxies bend light passing nearby by more than their visible mass could account for. The pattern of the oldest light in the universe carries the fingerprint of extra mass that emits nothing at all. Add it up, and roughly 5/6 of the matter in the universe is invisible. It does not shine, absorb, or reflect. Its only known interaction is gravity, and gravity is far too weak to detect for anything smaller than a planet. So detection experiments hunt for the rare occasion when a dark matter particle strikes an ordinary atom and deposits a scrap of energy. Those experiments are enormous. Tanks of liquid xenon weighing tons, buried in mines, surrounded by water and shielding, watching for a handful of flashes per year. The heavy candidates have been hunted this way for decades with no confirmed sighting, and attention has been drifting toward lighter possibilities. Light particles are harder, because a light thing striking a heavy nucleus transfers almost nothing. Throw a ping-pong ball at a bowling ball and the bowling ball barely notices. The energy deposit falls below what any of the big detectors can register, which points toward instruments that notice absurdly small amounts of energy. A superconducting qubit array is exactly that. It responds to essentially every cosmic ray that passes through it. It registers disturbances far too faint for conventional detectors. It can be arranged in a grid, with each element reporting separately, so a real event lights up a pattern of neighbours while random noise does not. And these machines are already being built in large numbers, funded by an industry chasing computation. The proposal that follows is elegant. Take a processor, put it deep underground where cosmic rays are blocked, shield it thoroughly, characterize every source of ordinary radiation until you know your background precisely, and then watch for events that fit nothing on the list. The same hardware, running the same monitoring routines, doing particle physics between calculations. There is a beautiful pattern here that runs through the history of science. Radio astronomy began when two engineers hunting a hiss in a communication antenna found the leftover glow of the Big Bang. Penicillin came from a contaminated dish nobody meant to grow. Something ruins your measurement. You chase it down. It turns out to be the universe telling you something. Quantum computers may follow the same path, becoming detectors for the invisible majority of matter because their sensitivity to noise made them impossible to shield. Which brings us to the last experiment in this story, and the largest claim in the field. Because in 2025, a team took the most destructive property of these machines, the tendency for information to scramble beyond recovery, and turned it into an instrument. They did it by running the scrambling backwards. The idea is to destroy the information deliberately, then rebuild it, and listen for what refuses to come back. Google announced the result in October 2025, published in Nature, running on a processor called Willow that carries 105 qubits. The experiment used 65 of them. They called the technique quantum echoes. Start with a shout into a canyon. The sound spreads, bounces off 1,000 surfaces, and returns as an echo carrying information about the shape of the rock. That is ordinary measurement. Now do something impossible in a canyon. Shout. Let the sound scatter, and then reverse every reflection, so the sound gathers itself back together and returns to your mouth as the original shout. A quantum computer can do this, because every operation it performs has an exact inverse. Run the circuit forwards, then run each step backwards in reverse order, and the system returns precisely to where it began. The measurement lives in what you do at the turning point. The sequence goes like this. Evolve the system forwards, letting information from one qubit spread across the whole array in a tangle far too complex to track. Then reach in and disturb a single qubit. One tiny nudge in the middle of the mess, then run everything backwards. If nothing had been disturbed, the system would return exactly home. The nudge prevents that, and the difference between where you land and where you started is the signal. Physicists call the quantity being measured an out-of-time order correlator, and it is a measure of how thoroughly information is scrambled. Here is why the reversal matters so much. That single nudge is minuscule, and its effect on the final state is smaller still, easily buried under noise. Running the evolution backwards makes all the paths that carry information about the nudge arrive together, in step, adding up rather than cancelling. Constructive interference, used as an amplifier. The echo comes back louder than the whisper that caused it. The measurement itself is why the team pushed this so hard. Every earlier demonstration of a quantum machine beating a classical one produced a list of bit strings, a pile of random-looking output whose statistical properties were the answer. Run it again on a different machine and you get different strings. Checking whether the answer is right is a nightmare, and those results generated years of dispute. An out-of-time order correlator produces a number. It is an expectation value, in the same family as a current or a magnetization. Any quantum computer running the same experiment should get the same value, and a second machine can check the first. That reproducibility is what the team meant when they used a word that had never applied to a quantum advantage claim before: verifiable. Making that claim stick meant surviving an assault, and the team ran the assault against themselves. The number that made headlines was 13,000, and the number that should have made headlines was 9. Start with the headline. The team ran their echo experiment on Willow, and it took about 2 hours. They then estimated how long the same computation would take on one of the fastest supercomputers in existence. 13,000 times longer. 2 hours against roughly 3 years of continuous supercomputer time for a single measurement. Now the second number, which is where the real work went. Claims like this have a bad history. The 2019 result announced a task that would take 10,000 years classically, and within months rival groups had produced smarter classical algorithms that shrank the estimate dramatically. The lesson stung. An advantage claim is only as strong as the effort spent trying to break it, so Google attacked its own result first. The team spent an estimated 10 person-years on what they described as classical red teaming, which means deliberately trying to find a conventional method that could reproduce their answer. They implemented 9 separate classical simulation algorithms, including approaches that compress the quantum description into a more manageable form and methods that sample cleverly, rather than calculating everything. All 9 failed on the higher-order version of the measurement. That is the strongest form of this kind of claim available today. It remains a statement about the algorithms that currently exist rather than a proof that no better one is possible, and the team said so. Outside reviewers quoted in the press called the work impressive, and pointed out correctly that previous advantage claims have been overtaken as classical methods improved. That caution is appropriate, and it is how the field is supposed to work. The part that reaches beyond the scoreboard is what the measurement can be used for. The team proposed something they call Hamiltonian learning. A Hamiltonian is the rulebook for a physical system, the description of how each part interacts with every other part. Knowing it means knowing everything about how the system behaves. For most real molecules, we do not know it. We have partial information from experiments and educated guesses for the rest. Here is the scheme. Take a real physical sample and measure echo signals from it using nuclear magnetic resonance, the same technology that produces medical scans. Then simulate those echo signals on the quantum computer for a proposed rulebook. Compare, adjust, repeat until the machine's predictions match what the physical sample actually does. At that point you have the rulebook, and with it the structure. A companion paper described applying this to nuclear magnetic resonance data to extract molecular structure. The applications the team pointed toward a drug discovery, where knowing exactly how a candidate medicine binds to its target is the central problem, and materials science for polymers and battery components. The same technique reaches in the other direction too. Scrambling of this kind is the phenomenon physicists argue about when they argue about information falling into black holes, a chip in a refrigerator measuring the thing that happens at an event horizon. Which leaves one question: and it is bigger than any single experiment. What is a machine when it starts telling you things you cannot check? We built a calculator and it turned into an eye. Look back across everything in this story and one thread runs through all of it. Every single result came from people who stopped asking what the machine could compute and started asking what it could become. A rhythm that thermodynamics forbids, holding steady in 20 loops of aluminum. 51 atoms refusing to forget where they started. A phase of matter that exists only while something shakes it. A current with no reverse gear. Objects that belong to neither family the universe was supposed to contain, changing type while being watched. A scrambled signal, reversed and amplified into a measurement of a molecule. None of that was on anyone's roadmap in 2019. There is a reason it happened this way, and it is worth stating plainly. For 4 centuries, physics worked by building better eyes for a universe that was already there. Telescopes found what the sky contained. Microscopes found what matter contained. Colliders found what particles contained. Every instrument answered the same style of question. What is out there? A programmable quantum processor answers a different question. What is allowed? You write down rules, and the machine builds a system that obeys them. If nothing in nature has ever assembled itself that way, the machine does it anyway. The catalogue of phases of matter stops being a list of what the universe happened to make, and starts being a list of what the mathematics permits, and that second list is enormously longer. Which puts theory in an unfamiliar position. For most of the last century, theory ran ahead. Predictions sat in journals for decades waiting for experiments to catch up. Gravitational waves waited 100 years. The Higgs waited nearly 50. The order has flipped. These machines are now producing results in regimes where nobody can check the answer by hand, because checking would require the classical computation that the machine was built to outrun. Physicists are working with an instrument that reaches further than their ability to verify it independently, which is why so much effort now goes into results that can be confirmed by a second machine rather than by a calculation. That is a new relationship between humans and their tools, and the field is still working out how to handle it honestly. What it means for the rest of us is more concrete than it sounds. The molecules in every medicine you have ever taken were understood through approximation, because the exact quantum description was beyond reach. The materials in batteries, in solar cells, in the magnets inside the machines that scan bodies, all of them designed by trial and educated guesswork. An instrument that computes what those systems genuinely do, rather than what our approximations suggest, changes the pace of that work. And it started with a chip that was asked to keep time, and answered with a rhythm of its own choosing. 20 loops of metal colder than anywhere in space, keeping a beat that the second law of thermodynamics had spent 150 years insisting was impossible. Nobody programmed the beat. The machine found it,